Assalamu alaikum friends. I am Taqdees Ahmed Siddiqui with Computer Graphics for Bachelor's in Computer Science course being offered by a virtual university, Government of Pakistan. This is our 44th lecture today, and we are talking about some OpenGL implementations. Today we shall be continuing our discussion and we will be taking it up to the usage of different commands of OpenGL to implement curves and surfaces. So let's begin. Today we shall be talking about evaluators for curves and surfaces. What is an evaluator? Well, actually OpenGL would be facilitating calculation of different vertices with their specific details, including their color and certain other details like the coordinates themselves, making use of certain commands. Now, these commands are going to help us implement the very concept of curves as well as surfaces. The theoretical background that we have built for curves, making use of our discussions on Bezier curves to be specific, would be extended to cover some aspects of surfaces as well. Precisely, we will be talking about implementation of Bezier surfaces as well. A Bezier curve is a vector valued function of one variable. We can say C of u expressed as x of u, y of u, and z of u, where u varies in some domain, say from 0 to 1, as we have been taking this in our previous discussions as well. A Bezier surface patch is a vector valued function of two variables, and we can write it as s of u comma v, defined using x of u comma v, y of u comma v, and z of u comma v, where u and v can both vary in some domain. The range isn't necessarily three-dimensional as is shown over here. We have talked about Bezier curves being functions of a single variable. U is the variable that we have been precisely using. And you would recall our basic discussion about the Bezier curves, in which we said that this is a specific type of curve in which we only interpolate the starting and the ending of the control points, and the rest of the points in between the first and the last, they only are used to approximate the shape of the curve. They are not actually interpolated by the curve. So those very curves are going to be our topic of discussion today, but today we will be implementing such curves, making use of commands available in OpenGL. For each u or u and v in case of the surfaces, the formula for C or S calculates a point on the curve or the surface, and that is known as an evaluator that would be available to us as a function in OpenGL. To use an evaluator, first define the function C or S, enable it, and then use the GLEVAL_1 or GLEVAL_2 command. As you would very well be able to guess that, of course, this suffix 1 and 2, they would be indicating the one dimension and the two dimension. To be very specific, they will be concerned with evaluating the coordinates, the vertices, for curve or for a surface, respectively. This way, the curve or surface vertices can be used like any other vertices to form points or lines. In addition, other commands automatically generate series of vertices that produce a regular mesh uniformly spaced in U or in U and V. When we were talking about the Beziers, you would recall that we did mention making use of a step value while moving from one point to another, while we were using the middle pointing approach. We were finding a middle point between the two consecutive control points, and for that we used this value of u ranging from 0 to 1 in uniform steps. We incremented u in uniform steps in order to be able to come up with equally spaced points on the curve. But it was not necessarily ensured, but of course the intervals that we used for u were surely evenly paced. One and two dimensional evaluators are similar in nature, but the description is somewhat simpler in one dimension. So this is what we are going to discuss first. So we are going to take a start with the one-dimensional evaluators, which would be concerned with evaluating the vertices for curves, not the surfaces. This section presents an example of using one-dimensional evaluators to draw a curve. It then describes the commands and equations that control these evaluators. One-dimensional example. We're going to start with a simple Bezier curve. The program shown in example 1 draws a cubic Bezier curve using 4 control points, as is shown in the figure. As you can see in this figure, first and the last of these points is being interpolated by the curve, and the 2 more control points in between, they are being used to approximate the shape of the curve. In our discussion on Bezier curves, we have talked about ways that we can employ to change the shape of the curve, and how changing the position of these control points has an impact on the shape of the curve. And whenever we want the curve to be skewed to one side or the other, what are different methods or mechanisms that can be employed. But right away, we are going to talk about only this simple cubic Bezier curve drawn making use of 4 control points. So this Bezier curve with 4 control points can be drawn using the code that follows now. We of course start with our typical includes, and then we define our control points array of the size 4 by 3 to hold these values. So the 4 control points with 3 coordinates for each of the points x, y, and z would be accommodated in this 4 by 3 array, followed by the definition of our init function, which starts of course with GL clear color with all zeros. Then GL shade model is specified to be GL flat, and then GL map 1f is called with the parameter GL map 1 vertex 3, 0, 1, 3, 4, and address of control points 0, 0. So the very first control point's address is being passed. GL enable is called next with the parameter GL map 1 vertex 3. Then the display function is coded, which starts of course with GL clear, and GL color buffer bit is passed as the parameter, and then we call GL color 3f with 1, 1, 1 as the 3 parameters. GL begin for GL line strip is called next, and that goes for I is equal to 0 to 30, incrementing I by 1 in each step. We call GL eval coord 1f, and it is passed as parameter a value of I over 30, with I of course typecasted as GL float in order to appropriately match the requirement of the float version of this function, GL eval coord 1f, and then GL end of course. And then the next part of the code displays the control points as dots. So this one would be creating the coordinates, the information that we want the evaluator to give us, that would be provided, and the next part would be drawing the control points so that they are also visible in our output. So for that, the first thing that we do is we set the GL point size to 5. Then you can see a call to GL color 3f with 1, 1, 0 passed as the 3 parameters, and then GL begin for GL points works for the 4 points. For I is equal to 0 to less than 4, for the values 0, 1, 2, and 3, it would be executed, and each time we would be calling GL vertex 3fv, the vector version, and it would be passed the address of the corresponding control point. When we begin with i's value equal to 0, therefore the first call would be made for the control point 0, 0. Next would be made for control point 1, 0, and then 2, 0, and then finally 3, 0. So the 4 points would be drawn with the point size 5, which is going to make them evidently visible. Finally, we say GL flush to end the function. Then the reshape function, using the arguments width and height as ever, calls GL viewport with the parameters 0, 0, width, height, with w and h, the width and height, of course typecasted as GL size I. And then we set the GL matrix mode to GL projection, and GL load identity is called, so that we have safe application of our projection information. If width is less than or equal to height, then calls to GL ortho are made with the parameters -5, 5, and -5 times h over w, both typecasted as GL float, comma 5 times h over w, comma -5, comma 5. Otherwise, if width is greater than height, then we call GL ortho with the parameters -5.0 times w over h, 5 times w over h, with both w and h typecasted as GL float, and then -5, 5, and -5, 5. And then we set the GL matrix mode to GL model view, and GL load identity is called. In the main, we start by calling glut init, and then glut init display mode, which is set using the bit mask glut single and glut RGB. Glut init window size is specified as 500, 500, and then glut init window position is given to be 100, 100. Glut create window is called next with the argument argv of 0. Then the function init is called, followed by the calls to the glut display func and glut reshape funcs using the parameters display and reshape, the functions that we have already defined, followed by the call to glut main loop before we return. A cubic Bezier curve is described by 4 control points, which appear in this example in the control points array. This array is one of the arguments to GL map 1f. All the arguments for this command are given next. GL map 1 vertex 3 is one of them. The 3-dimensional control points are provided, and what we get is 3-dimensional vertices. So the evaluator works like this, that it gets the 3-dimensional control points, and what it gives us as a result is the vertices information, which is again 3-dimensional vertices. Secondly, we have the low value of the parameter set to 0.0, and high value of parameter u is used as 1.0. The number of floating point values to advance in the data between one control point and the next is also specified as one of the parameters, so which tells us how we are going to move from one point to another, in what steps those values that we are going to use to increment and move on to the next control point, that is also specified as the parameter. Then the order of the spline, which is given by the degree plus 1, which in this case the degree is 3, so the order would be 3 plus 1, 4. So that is also specified. So you can recollect in our call that we had this parameter value 4 specified. So that 4 is actually for the order of the spline, which is 4 in this case, because degree is 3, 3 plus 1, 4. And then the address of the starting control point given by ampersand control points 0, 0, which is the pointer to the first of the control points data, that is also specified as one of the parameters. Please note that the second and third arguments control the parameterization of the curve as the variable u ranges from 0 to 1. And the call to GL enable enables the one-dimensional evaluator for 3-dimensional vertices. And that's what we want to do. We want to calculate the 3-dimensional vertices for our curve. The curve is drawn in the routine display. Now, since the evaluator is enabled, the command GL eval coord 1f is just like issuing the GL vertex command with the coordinates of a vertex on the curve corresponding to the input parameter u. So the very way we have been using the GL vertex command, we make use of GL eval coord 1f because it results in the same output. We get what we used to get with the GL vertex, and of course corresponding to the input parameter u, because input parameter u is going to have its values changing. Starting with 0.0, we are going to increment it in equal paces and ultimately reach 1. When u would be 0, of course we will be starting with the first of the control points, which would be actually interpolated, and when we will end at u equaling 1, we'll be ending with the last of the control points, which would again be actually interpolated, and all the points in between would only be approximating the shape of the curve. The Bernstein polynomial of a degree n or order n plus 1 is given by the expression b I comma n of u equals number of times I can be sampled from n times u raised to power I times 1 minus u raised to power n minus I. Now if pi represents a set of control points 1, 2, 3 or even 4 dimensional, then the equation p of u equals summation of pi bi comma n of u for I is equal to 0 to n represents a Bezier curve as u varies from 0 to 1. To represent the same curve but allowing u to vary between u1 and u2 instead of 0 and 1, we'll have to evaluate u minus u1 over u2 minus u1. By default, we have been talking about the simplest case in which we say that u will be having its values between the range 0 to 1, which is what we have been using as well in our previous theoretical examples. But practically, we have the option of specifying different values for this range. So the starting value for u can be specified using u1, and the last maximum value can be specified using u2. So we can make use of u1 and u2 to specify the range that u can vary between. The command glmap1 defines a one-dimensional evaluator that uses these equations, the very ones that we've just seen for the Bezier curves. The target parameter specifies what the control points represent, as is shown in the table. The table you are going to watch in a short while. And therefore, how many values need to be supplied in points. So taking a look at the table, we'll be able to see what these control points are representing depending upon the target parameter. The points can represent vertices, RGBA color data, normal vectors, or texture coordinates. So you will see that the points that we get can at one point in time or the other give us vertices, RGBA color data, or normal vectors, or even texture coordinates. Look at this table closely and you'll be able to appreciate. This gives us the types of control points for glmap1 and its variations. The parameter glmap1 vertex 3 means that we are talking about the XYZ vertex coordinates. So when used, we'll be getting the XYZ vertex coordinates from our evaluator. glmap1 vertex 4 when used would mean that we talk about X, Y, Z and W vertex coordinates. glmap1 index means color index specification. glmap1 color 4 means RGBA, the 4 component colors. glmap1 normal gives us normal coordinates. glmap1 texture coord 1, 2, 3 and 4 specifically are talking about the texture coordinates S, ST, STR and STR and Q respectively. So for example, with glmap1 color 4, the evaluator generates color data along a curve in 4-dimensional color space, or to be precise, RGBA. We also use the parameter values listed in the table to enable each defined evaluator before we invoke it. We pass the appropriate value to GL to enable it, or GL disable in order to disable the evaluator. Depending upon what we want, we can specify the parameters accordingly. If we will be looking forward to generating the vertex coordinates, those can be had, or if we talk about their color values, those can be had, or even the texture map coordinates can also be generated using the same evaluator. The next two parameters for glmap1, which are u1 and u2, they indicate the range for the variable u. u1 tells us the initial value that u can have, and u2 would be the final value that u can be given. Thus, it's an offset value between the beginning of one control point and the beginning of the next control point. Whenever we talk about the calculation of points in between the two control points, making use of the concept of in-betweening, so we specify what step we are going to move from one u value to the next u value in order to come up with the next point on the curve. Of course, right now we are talking about the curves only. Later on, we would be extending the idea to surfaces, where we will be seeing that, okay, we can approximate a surface in the form of multiple curves that are maybe cross-sectional with each other, forming a wireframe-like image for the surface. The order is the degree plus 1, as we have stated earlier as well, and it should agree with the number of control points that are being used. The parameter points actually points to the first coordinate of the first control point. As we've seen earlier, that we pass this as the last of the parameters, the address or the pointer to the first of the control points. In this case, we had 4 control points which we kept in an array, and we passed the address of the first of those control points as the last parameter. Using the example data structure for GL map 1 and its variations, we can use the following 4 points. The control points 0.x, pointer to it, address of control points 0.x, typecasted as a GL float pointer. Please do note the parameter values in the table that we have seen, which when specified would be resulting in appropriate desired output, which could be coordinates of the vertices, or the color index, or the color value, or the normal coordinates, or the coordinates of the texture map. More than one evaluator can be evaluated at a time. If we have both a GL map 1 vertex 3 and a GL map 1 color 4 evaluator defined and enabled, then calls to GL eval coord 1 generate both a position and a color. Making use of these parameters that are given in the table would definitely be interesting, because we do require at one point in time or the other the coordinates of the vertices for the points on the curve and the colors as well. So if we require both of them, we can have 2 evaluators active at the same time and call to GL eval coord that is going to result in generation of the vertices data as well as the color information. So we can make use of multiple of these at the same time as well. Only one of the vertex evaluators can be enabled at a time, although we might have defined both of them. Similar is the case when only one of the texture evaluators can be active at a given time. At any point in time, we can only have one evaluator for vertices evaluation. Although define हम दोनों कर सकते हैं, लेकिन एक वक्त में enabled एक ही होगा, और उसके ज़रिए से हम कैलकुलेशन करने के बाद फिर उसको डिसेबल करके दूसरे को enable करके उसकी कैलकुलेशंस कर सकेंगे. एंड सिमिलरली टेक्सचर इवैल्यूएटर्स जो हैं वो भी एक वक्त में एक ही एक्टिव हो सकता है. Other than that, however, evaluators can be used to generate any combination of vertex, normal, color and texture coordinate data. So it's not necessary कि इनमें से सिर्फ 2 ही या सिर्फ कोई एक ही या सिर्फ 3 ही या किसी स्पेसिफिक ऑर्डर में ही जनरेट हो सकते हैं. हमने जो डेटा हमें रिक्वायर्ड है about our vertices, the coordinates, the color information, vertex normal, they can all be calculated making use of these evaluators. If more than one evaluator of the same type is defined and enabled, the one with the highest dimension is used. Now use GL eval coord 1 and its variations to evaluate a defined and enabled one-dimensional map. And that can be done like this. That GL eval coord 1 f or d is called with the parameter u passed as its argument. Void GL eval coord 1 f or d v vector version makes use of pointer to u, and then this causes evaluation of the enabled one-dimensional maps. For evaluated vertices, values for color, color index, normal vectors, and texture coordinates, they are generated by evaluation. As said earlier, we can make use of the evaluator to get any of the four values: the vertices, colors, color index, normal vectors, and even the texture coordinates. Calls to GL eval coord do not use the current values of color, color index, normal vectors, and texture coordinates. So actually GL eval coord leaves these values unchanged. So it doesn't make use of the current values. It comes up with the new values that we generate using the appropriate parameters. Defining evenly spaced coordinate values in one dimension, that can be had by using GL eval coord 1 with any values for u. But by far the most common use in this is evenly spaced values, as is shown in the previous example. So we can have the option of unevenly spaced values, but typically the algorithms that we have been looking at and the implementations also speak of the same. The typical usage is the evenly spaced values, and that is normally what we use. Although we don't insist that we always have to use the evenly spaced values, but it is simpler to make use of the evenly spaced values. To obtain evenly spaced values, define a one-dimensional grid using GL map grid 1, and then apply it using GL eval mesh 1. So you'll be defining the grid using the function, the command GL map grid 1, and that would be applied later on using GL eval mesh 1. The way we write the map grid function is that GL map grid f or d makes use of GL int n and then u1 and u2, the two parameter values giving the range for u. Now this defines a grid that goes from u1 to u2 in n steps, which are evenly spaced. Void GL eval mesh 1, on the other hand, makes use of GL enumerated mode and GL int p1 and p2. Now this applies the currently defined map grid to all enabled evaluators. The mode can be either GL point or GL line. So the first parameter, that can be GL point or GL line, and it would depend upon whether we want points to be drawn or we want connected lines along the curve drawn. So depending upon what we want, we can either use GL point as the mode or GL line, which would of course result in drawing the points that we calculate the coordinates for, or would be connecting them as line segments to come up with the continuous curve. The P1 and P2 parameters of course would be the starting and the ending control points. The call has exactly the same effect as issuing GL eval coord 1 for each of the steps between points and including P1 and P2, where P1 is greater than or equal to 0 and P2 is lesser than or equal to n. So the same effect that we had from the grid and then application of the grid using mesh, that can be had making use of the same good old GL eval coord 1 function, and that command can be issued for all the steps between P1 and P2, where P1 and P2 would also be inclusive, and all the steps in between that we are going to have from 0 to n, they would be incorporated, and we'll be getting the same effect, the same resultant. Programmatically, it is equivalent to this code: GL begin, GL points, for I is equal to P1 to P2, incrementing I by 1 every time, we call GL eval coord 1 with the parameter u1 plus I times u2 minus u1 over n, GL end. Except that if I is 0 or I is equal to n, then GL eval coord 1 is called with exactly u1 or u2 as its parameter. So for all other values other than the 0 and n, the same code would work, but for when I is equal to 0 or when I is equal to n, we will be calling the same function GL eval coord 1 using u1 or u2 respectively as its parameters. We have talked about the one-dimensional evaluators thus far. Now we are going to talk about the two-dimensional evaluators, and these are similar in nature to the one-dimensional evaluators. You'll shortly see that the usage is also kind of similar. We have only introduced the concept of yet another dimension. So we are not only concerned about the curves now, but we are concerned about the surfaces and surface patches. So that's what we want the different vertices for calculated, and in this calculation the two-dimensional evaluators are going to help us. In two dimensions, everything is similar to the one-dimensional case, except that all the commands must take two parameters, u and v. Now these two parameters, as opposed to the one parameter for one dimension, are going to be used everywhere whenever two-dimensional evaluators shall be brought into play. Points, colors, normals or texture coordinates must be supplied over a surface instead of a curve. Of course, now we are talking about surfaces, we are not talking about just the curves. So the relevant data which was earlier on referenced with reference to the curve would be now used with reference to the surface. Mathematically, the definition of a Bezier surface patch is given by the equation S of u comma v equals sigma for I is equal to 0 to n of summation for j is equal to 0 to m of b I comma n of u, b j comma m of v, p I j, where the p I j are a set of m by n or m times n control points, and the b I are the same Bernstein polynomials as we used for one dimension. So this equation gives us a Bezier surface patch. The procedure to use two-dimensional evaluators is similar to the procedure for one dimension. As stated earlier, the first step would be to define the evaluators with GLMAP2. Recall that we used GLMAP1 in case of one-dimensional evaluators, but for two-dimensional evaluators we'll be using GLMAP2. Secondly, enable them by passing the appropriate value to GLEnable. Having defined, we have to enable it as well. Next step is to invoke them either by calling GLEvalQuad2 between a GLBegin and GLEnd, or by specifying and then applying a mesh with GLMapGrid2 and GLEvalMesh2. तो जिस तरह से हमारे पास वन डायमेंशनल के केस के अंदर दोनों ऑप्शंस मौजूद थी कि हम इवैल कोऑर्ड्स का तरीका इस्तेमाल करें बिटवीन अ लूप बिटवीन जीएल बिगिन एंड एंड, या फिर हम जीएल मैप ग्रिड और फिर मैश अप्लाई कर लें, वही तरीका यहाँ पर भी इस्तेमाल हो सकता है. वी कैन मेक यूज ऑफ इवैल्यूएशन ऑफ कोऑर्डिनेट्स एक्सप्लिसिटली जीएल इवैल 2 के जरिए से, या फिर हम पहले ग्रिड डिफाइन करें और फिर उसको अप्लाई करें यूजिंग द मैश फंक्शन. But of course, we'll be making use of these values, the GLEvalQuad or the GLMapGrid2 and GLEvalMesh whenever required. We can do it explicitly using quads, or we can use it, do it implicitly, making use of the definition of map and then application as a mesh. Defining and evaluating a two-dimensional evaluator is what comes next. We use GLMAP2 as stated earlier and GLEvalQuad2 to define and then invoke a two-dimensional evaluator. And the syntax goes like void GLMAP2 f or d using the parameter GLEnumerated target followed by u1 u2 followed by an integer specifying u stride, another integer specifying u order, followed by v1 and v2, and then integer v stride and integer v order, followed by the points. So these are the parameters or arguments that would be supplied when calling GLMAP2. The target parameter can have any of the values in the table 1, except that the string map1 is replaced with map2. Since we are now talking about two-dimensional evaluator, so wherever we had 1 indicating the one-dimensional evaluator, that would be replaced with 2. सो मैप वाली कमांड के अंदर भी जहां पे मैप 1 था वहां पे हम मैप 2 यूज कर रहे होंगे. मिनिमम एंड मैक्सिमम वैल्यूज फॉर बोथ u एंड v दे आर प्रोवाइडेड यूजिंग u1 u2 v1 एंड v2. सो u की वैल्यूज होंगी फ्रॉम u1 टू u2 और v कैन वेरी फ्रॉम v1 टू v2 बिकॉज नाउ वी आर टॉकिंग अबाउट द 2 डायमेंशंस जहां पे हमने ये कहा था कि विल बी डीलिंग विद 2 वेरिएबल्स as opposed to 1 which was only u in case of 1 dimension. The parameters ustride and vstride indicate the number of single or double precision values allowing users to select a subrectangle of control points out of a much larger array. So we have the facility of choosing a subset or a subrectangle of the total number of available points. For example, if the data appears in the form GL float control points 100, 100, 3 and we want to use the 4x4 subset beginning at the control points 20, 30, then we can choose ustride to be 100 times 3 and vstride to be 3. The starting points should be set to ampersand control points 20, 30, 0 because that would be giving us the address to the very first point that we want to include in our 4x4 subrectangle. Finally, the order parameters u order and v order can be different, allowing patches that are cubic in one direction and quadratic in the other. So this is also possible because of these two parameters. We can have different order for u and v. For example, void GL eval coord 2 f or d can be called with u, v as the parameters, and void GL eval coord 2 f d with vector variation, the vector version, can be called with a pointer to these values. So if we are going to specify specific values u and v, we can make use of the non-vector version, and if we are going to specify range of values, we can use the vector version. Now this causes evaluation of the enabled 2-dimensional maps. The arguments u and v are the values or a pointer to the values u and v in the vector version of the command as stated earlier. If either of the vertex evaluators is enabled, GL map 2 vertex 3 or GL map 2 vertex 4, then the normal to the surface is computed analytically. This normal is associated with the generated vertex if automatic normal generation has been enabled by passing GL autonormal to GL enable. So the normals associated with these vertices would be automatically calculated if we have enabled automatic calculation of normals. And normals we definitely require, as we have seen earlier as well, that whenever we are applying different lighting and lighting equations and lighting models, we do require information on these normals. So while defining surfaces or surface patches, we can evaluate and calculate their surface normals or vertex normals as well. If it's disabled, the corresponding enabled normal map is used to produce a normal. If no such map exists, the current normal which is available is used. Now we are going to talk about a 2-dimensional example. The example would be, of course, now coming up with a Bezier surface patch. Earlier on, we talked about a Bezier curve. Example 2 draws a wireframe Bezier surface using evaluators as shown in the next figure. In this example, the surface is drawn with 9 curved lines in each direction. Each curve is drawn as 30 segments. To get the whole program, we can add the reshape and the main routines as we used in example 1. This is the figure that shows the Bezier surface that we'll try to draw now. This uses 9 curves in the both directions, and each one is segmented into 30 segments. Example would of course start with our typical includes, followed by the control points array defined as a 4 by 4 by 3 array, which would be appropriate to hold the values, Void display void, the display function of course starts with declaring integers I and j, and the first call is made to GL clear, GL color buffer bit and GL depth buffer bit supplied as arguments, followed by GL color 3f set to 1 1 1, and then we use GL push matrix. GL rotate f is called next with the parameters 85.0, 1.0, 1.0, 1.0. I hope you would be able to recall the use of GL rotate f, in which we specify the angle of rotation first, and then we tell the coordinates of the point which would be used to determine the axis around which we need this rotation to be performed, and that is calculated using a ray that starts at the origin and reaches the specified xyz coordinates point. For j is equal to 0 to 8, we increment j by 1 each time. From 0 to 8 we will be having 9 different values, and we say GL begin with GL line strip for I is equal to 0 to 30, the 30 segments that we talked about in each line, that would be taken care of over here. We make calls to GL eval coord 2f with the parameter I by 30 and j by 8, with both I and j typecasted as GL float. So we will be calling GL eval coord 2f 30 times for each of the lines, each of the 9 lines that we are talking about. Then GL begin GL line strip for I is equal to 0, I up to 30, I less than equal to 30, we increment I by 1 each time, and we call GL eval coord 2f, and this time we pass it j over 8 comma I over 30 as parameters, with both j and I of course typecasted as GL float, and then GL end, and finally we say GL pop matrix and flush. In init we start with GL clear color specified as all zeros, followed by GL map 2f, which makes use of the argument GL map 2 vertex 3 comma 0 1 3 4 0 1 12 4, and finally the address or the pointer to the starting control point, ampersand control points of 0 0 0. Try to map all these values onto the basic form of GL map 2f that we discussed earlier on, and see what each of these parameters stands for, and what are we talking about when we are using a 4 over there and a 12 later on. GL enable GL map 2 vertex 3. So having defined it, we enable the map. GL map grid 2f is passed parameters 20 0 1 20 0 1. GL enable GL depth test is called next, followed by GL shade model GL flat. So we'll be using flat shading. Next we'll be discussing defining evenly spaced coordinate values in 2 dimensions. We have talked about this issue in 1 dimension, how we can specify evenly spaced values, but now when we are talking about 2 dimensions, we are talking about making of the surfaces. Let's revisit the same issue from 2 dimensions perspective. In the 2 dimensions, the GL map grid 2 and GL eval mesh 2 commands are similar to the 1 dimensional versions, except that both u and v information must be included and specified over here. When we were calling GL map grid 1 and GL eval mesh 1, we were only specifying u, because that was the only independent variable in terms of which we were defining the curve. But in terms of u and v, we are defining the surface. Therefore both u and v will have to be supplied when we are talking about making use of GL map grid 2 and GL eval mesh 2. Void GL map grid 2 f or d would be passed GL int nu u1 u2 as parameters, along with GL int nv v1 and v2. So the 2 variables u and v, they are being specified, and also we are telling what would be the starting and ending value for u, and similarly for v. the first and the last value, between which the u can have its value varied or v can have its values varied. So that is also specified. Then GL eval mesh 2 makes use of GL enumerated mode and I1, I2, J1, J2. This defines a two-dimensional map grid that goes from U1 to U2 in NU evenly spaced steps and from V1 to V2 in NV steps. GL map grid 2, and then it applies this grid to all the enabled evaluators using GL eval mesh 2. We have specified U and we have specified V and we have specified their range. So while moving for U, while moving from U1 to U2, we are going to have evenly spaced steps, and similarly while moving for V from V1 to V2, we are going to have again evenly spaced steps, and those are going to result in the required information that we are looking for to build the Bezier surface, and that information would be defined as a grid and applied using the mesh. The only significant difference from one-dimensional versions of these two commands is that in GL eval mesh 2, the mode parameter can be GL fill as well, and it can also be GL point or GL line. In case of curve, there was no concept of filling. There was the concept of color associated with it, but filling का concept वहाँ पे नहीं आ सकता था because we were talking about points that were joining hands together or line segments that were connected together to form the curve. But whenever we walk into the two dimensions, we walk into the making of surfaces, now we can also specify a fill color for that surface, how that surface needs to be filled. We can specify a flat fill as we did earlier on, or we can make use of some other shading, maybe Gorau shading, and we could come up with some very, very natural looking surfaces or surface patches. GL fill generates filled polygons using the quad mesh primitive. Stated precisely, GL eval mesh 2 is nearly equivalent to one of the following three code fragments that you're going to see now. It's nearly equivalent because when I is equal to NU or J is equal to NV, the parameter is exactly equal to U2 or V2, but not to U1 plus NU times U2 minus U1 over NU, which might be slightly different due to the round off error. So the first code segment makes use of GL begin, GL points, runs two loops. The first one for I is equal to NU1 to NU2, incrementing each step by 1. The inner loop for J is equal to NV1 to NV2, incrementing J by 1 in each step, and calling GL eval quad 2 for U1 plus I times U2 minus U1 over NU, comma V1 plus J times V2 minus V1 over NV. Or we can write this code running this loop for I is equal to NU1 to NU2, incrementing 1 each time, GL begin GL lines for J is equal to NV1 up to NV2, incrementing J by 1 each time, call GL eval quad 2 for U1 plus I times U2 minus U1 over NU, or comma V1 plus J times V2 minus V1 over NV. Notice we are using GL lines over here, but this would be followed by repeating the same couple of loops for GL lines, but this time calling eval quad 2 for U1 plus I times U2 minus U1 over NU, comma V1 plus J times V2 minus V1 over NV. For I is equal to NU1 up to NU2, incrementing I by 1 each time, we can have GL begin for GL quad strip, and that would be running the loop for J is equal to NV1 to NV2, incrementing J by 1 each time, GL eval quad 2 called for U1 plus I times U2 minus U1 over NU, and similarly for V. And GL eval quad 2 called again for U1 plus I plus 1 times U2 minus U1 over NU, and V1 plus J times V2 minus V1 over NV. Although these three code segments that we have just seen are equivalent in effect to our call to GL mesh, but it is always advisable to go for making use of the definition of grid and then application using the mesh, because it would be more efficient that way. So folks, we have talked about curves and we have talked about surfaces, and we have seen how we can build them making use of commands available in OpenGL. We can still continue talking about the surfaces and the filled surfaces because it is a very fascinating topic, but you can always go ahead and explore different other variations. As I just mentioned, that instead of using flat shading, we could make use of certain other types of shading, like Gorau maybe. So you could go ahead and experiment with it, filling the surfaces and surface patches. The one that we've just made is only a grid. Next time, we would be coming up with, hopefully, another advanced, exciting topic. But that, of course, would be it, because that would be our last lecture, hopefully. तब तक के लिए इजाज़त दीजिएगा. फ़ी अमान अल्लाह.